the moon is weird. It's completely unlike anything else in the solar system. So how did our planet end up with such a special moon? The answer is that, surprisingly enough, the moon is a piece of our planet. There's a lot going on with the moon. For starters, it exists, which is weird in its own way. Mercury has no moons, and neither does Venus. Mars does have 2 moons, but they're really just captured asteroids. Earth is the only rocky planet in the solar system with a significant moon. And the moon really is significant. It's roughly 1.2% the mass of Earth. That may not be big in an absolute sense, but for the solar system, that's huge. No other moon is that large relative to its parent planet. The oddities don't stop there. The total angular momentum of Earth's spin, the moon's spin, and the moon's orbit is very large, far higher than for any other terrestrial planet. So how did we get so much momentum? Plus, the moon is full of KREEPs, that is, potassium, rare earth elements, and phosphorus. These elements don't usually like to hang out together, but lunar samples show that they are often mixed. That requires the moon to have been molten at some point, which takes a lot of energy. And the real icing on the cake is that the moon has many of the same abundances of stable isotopes as Earth does, which indicates that Earth and the moon evolved from the same clump of material. The leading explanation for all of these mysteries is known as the giant impact hypothesis. According to this story, when the solar system was just getting started, a Mars-sized protoplanet named Theia slammed into the proto-Earth. With an impact velocity of somewhere around 20,000 miles per hour, 32,000 kilometers per hour, relatively slow as impacts go, what happened next was nothing short of catastrophic. The heavy core of Theia sank deep into Earth, enlarging our planet's core. The 2 bodies' mantles mixed and thus bulked up our planet, and the crusts were scattered far into space. What happened next is a little hard to follow and depends a lot on exactly how the impact unfolded and what Theia was made of. But the general picture is that some stuff went flying away, never to return. Other stuff rained onto Earth's surface, and a big chunk remained in orbit. In as little as a few hours, or perhaps up to a century or more, that material coalesced into its own solid object, the moon. Some models suggest that a second moon, just a few hundred kilometers across, formed past the far side and then slowly approached the moon and pancaked itself. This would explain why the far side of the moon is lumpier than the near side. There's also the possibility that this wasn't a low-energy, glancing blow at all, that instead, the proto-Earth was spinning really quickly, and then got nailed by Theia. This would have delivered more than enough energy to vaporize everything and create a donut-shaped ring of plasma known as a synestia. No matter what, this impact released a lot of energy, more than enough to turn the moon into a molten ball, more than enough to bring the KREEP elements together, and more than enough to mix Earth's original material and Theia's to create a set of common features between Earth's crust and the moon. As with all hypotheses, it's not perfect. For example, if there's enough energy to liquefy the moon, there's enough energy to liquefy Earth's surface. But there is no evidence for large-scale magma seas in Earth's history. Also, the moon does have some volatile elements, like water, trapped in rock, but a giant impact giant-energy event should have gotten rid of those. Yet, dear explorers of the cosmos, let's not dismiss this grand narrative too hastily. The giant impact hypothesis, while bearing scars of imperfection, stands resilient amid a torrent of new evidence that ignites our imagination and reaffirms its profound truth. Picture this: a cataclysmic embrace billions of years ago. Not just a collision, but a cosmic rebirth that forged our silvery sentinel from the ashes of destruction. It's a story that tugs at the heartstrings of every stargazer, reminding us how fragility and fury can birth enduring beauty. Recent revelations have masterfully addressed those nagging doubts. The absence of widespread evidence for a global magma ocean on Earth. Geologists now point to subtle clues in ancient zircons and mantle rocks, whispering of a hellish, molten surface in our planet's infancy. a fiery crucible erased by time's relentless erosion, yet etched in the isotopic echoes we uncover today. And those volatiles, like elusive water trapped in lunar glass beads? High-energy models, including the mesmerizing synestia, a swirling, donut-shaped plasma cloud, suggest they weren't entirely banished. Some clung tenaciously, shielded in the chaos, or perhaps arrived later via cometary couriers, quenching the moon's thirst in a poetic postscript to the impact. But oh, the thrill of discovery intensifies with 2023's groundbreaking simulations. Scientists, wielding supercomputers like modern-day oracles, have unveiled remnants of Theia herself, buried deep within Earth's mantle as colossal, continent-sized blobs known as large low-velocity provinces, LLVPs. These seismic anomalies, denser and more iron-rich than surrounding rock, are Theia's undigested core fragments, silent witnesses to that ancient smash-up. Far from vanishing without trace, Theia endures, her essence bolstering Earth's core, perhaps even sparking the plate tectonics that cradle life. This isn't mere speculation. It's substantiated by seismic waves and geochemical fingerprints, painting a vivid portrait of a merged world. Moreover, fresh high-resolution models shatter old timelines. No leisurely coalescence over months. The moon may have sprung forth in mere hours, a satellite hurled into orbit from vaporized Earth material, explaining the uncanny isotopic twins we see between our worlds. Calcium and magnesium isotopes from Apollo samples corroborate this high-energy saga, timing the lunar magma ocean solidification to as little as 130 million years. A blink in cosmic terms, yet enough to mingle those enigmatic creeps. Alternatives? Fission from a spinning Earth, capture of a wandering body, or co-accretion in the solar nebula. They falter under scrutiny, unable to muster the angular momentum or compositional harmony we observe. No, the giant impact endures as our beacon, persuasive in its explanatory power, evoking awe at how violent sculpted serenity. Imagine standing on that nascent Earth, amid the glowing debris, witnessing the moon's fiery assembly. It stabilized our tilt, tamed our tides, and perhaps even nurtured life's fragile spark. This isn't just science. It's a testament to resilience, a love letter from the stars. The moon, born of Earth's shattered embrace, calls us to wonder, to explore, to cherish our shared odyssey through the void. In its craters and phases, we see our own turbulent origins, a reminder that from chaos comes companionship, eternal and profound. The giant impact hypothesis is the most compelling story we have for how the moon formed. And without a time machine into our distant past, we'll never be able to prove it. But it still fits almost all of the evidence we have so far, so it's a story worth keeping around.